All right, so how do vectors come into projectiles? Well, you have really two types of projectile. A projectile is an object which follows a path called a parabola. And it's got a symmetrical shape if it leaves level ground and falls on the same level ground. And you can split that motion into two. So this half is exactly the same as this half. And on the way up, that vector is affected by acceleration due to gravity. And it slows down at the same rate as acceleration due to gravity, 9.81 metres per second squared. But after it passes its halfway stage and its maximum height, it speeds up again and falls with an acceleration due to gravity of 9.81. And that's why its whole shape is a parabola, and that's symmetrical. Now, there are two parts to the motion, and what we do is we split. If you're told the velocity of the object initially, what we do is we split our motion up into horizontal components. I'm just going to draw those in green here. And that's your horizontal component. And then a vertical component, which I'll draw in red. Now, all that is what I showed you in the vectors podcast, is that you have got your vector there, and you're splitting it up into two components. The red one's up here, and the bottom one there is green. I'll just go over the top of this with green. And that's your horizontal vector, and this one is your vertical vector. So if you know the size of this angle, and you very often are given the size of the angle and the size of the velocity v, then you know immediately that this horizontal component of the velocity is v, and because it's beside it is the cos of the angle, and this one is the v, the sine of the angle. And once you know that, you treat that as if there are two individual bits going on there, two individual motions going on. But this vector, the shape of this is a combination of the two of them at every single point across there. So the next thing I would do when I start a vector question, a projectile question, I split it into the motion into a horizontal part and a vertical part. And the horizontal part, the things that I know its initial velocity, and it's always v cos theta. I know that it takes a certain length of time, and I also then can tell the distance from here to here horizontally. Now, I may not know that at the beginning, and I may not know the time at the beginning, but that's called the range. And that's the only things that I need to know about the horizontal motion. It's not affected by acceleration due to gravity, and therefore this velocity v cos theta should be the same at all parts of its motion. If you were to draw an arrow to represent that, you should be drawing the same length of arrow. And it's always pointing in the same direction. It always has the same size. So there's only one equation we would use with that horizontal, and that's velocity is distance over time, where the velocity we're using here is that value of v cos theta. So that's only one equation we need to use with the horizontal bits. Now the problem is very often at the start of the question, we only know v cos theta, we often don't know d and t, and therefore we can't use this to find a time until we've done something vertically. So vertically, what do we know? Now vertically is subject to equations of motion. And that you could use any one of the four equations of motion with that. And so what do we know? We know that the initial velocity of our vector from this diagram and here is v sine of theta. If this is perfectly symmetrical, then we also know the final velocity. And it's a negative of that. It's moving in a different direction. So it's minus v sine of theta. We know that it's subject to an acceleration due to gravity of minus 9.81. And unless you know that it's starting from the middle and moving down the way, I would always put that in as minus 9.81. And if it isn't right, then the direction that we thought, it'll come out as a minus answer. And we may have to find a vertical height. So that's a vertical height, which we probably don't know. And we may have to find a time. Now, the thing that's common to both these things is that the time has to be the same. So the time it takes to travel here vertically is exactly the same as the time it takes horizontally. So sometimes we have to work out a range. We know this, we don't know this, and we don't know this, but we can find a vertical time from our vertical components, and it's exactly the same time here. So you can use a combination of these two sets of equations and these two components to work out all the unknown things that you don't already know. Now, one last thing. If you are told something about the maximum height, and this applies vertically, maximum height is, of course, a vertical height. So I'm putting it over this side. If you know that, you always know that at the maximum height, if you're throwing an object up and it's coming back towards you, at the maximum height, its final velocity is 0. And in the projectile style question, the time taken to get to the maximum height is half the total time. The total time divided by 2. And so those are two things that you may know already, or you may have to work out. The second type of projectile is a projectile which is falling from a height. And the height that it may be falling from there is something like this. A cliff face, say, for example. You very, very often do know this height, but we'll just put it in as S, and that's a height. And you know that your projectile, you're generally given a horizontal velocity for that. So that's a horizontal velocity. And vertically, what's happening there, if you've got something being shot off the side of a cliff, vertically it's starting from rest and it's just dropping as if you were dropping something from rest out of your hand. So there's your horizontal velocity. There's your range now. And of course that's half the range if we had this going the whole way there. That's just half. So what do you know there? Well, horizontally, you'll know horizontal velocity. You'll just know its value. There's no sine or cosine theta here. So horizontally, you'll know its velocity probably. You may know a time, and you may know the horizontal distance is its range, and very often that's expressed as the distance from the foot of the cliff or the distance from wherever it's dropped from. So that's a range. Vertically, what do you know? You know the initial velocity is equal to 0 because this is just like dropping something at the same time that it's been shot outwards. And if you did drop something at the same time as another object which has been shot outwards like that, they would both hit the ground at the same time. No matter what their masses are, the mass is independent of the vertical motion. So U is equal to 0. V we don't know, we may have to calculate. The height is just the vertical height. You may be given that. The time, you probably don't know. And acceleration due to gravity, you always know, is 9.81. And you may have to do a calculation there of some description. Now, the last thing then to do with this, and I'm going to go on to another page, is the magnitude of the velocity when it hits the ground. Now, you'll always know this horizontal velocity will always stay the same as it hits the ground, but you may have to calculate your vertical velocity there using equations of motion. So to find the magnitude of the final velocity, what you will do then is you'll take your horizontal velocity and your final velocity and add them vectorially like you've done in the past. And so if I just draw these end to end, so you probably know the horizontal velocity which has stayed the same. You've had to calculate your vertical velocity from your equations of motion, and then the magnitude of the final velocity is just going to be the resultant of those two, which is that. So you use Pythagoras' theorem to find that, and we'll call it R. So R is equal to the square root of, I'll just call this V and that H standing for horizontal and vertical velocity. So H squared plus V squared. Last thing you might have to find is the angle of impact. And if you know the values of your horizontal velocity, your vertical velocity, and possibly you might now know your resultant, the angle of impact is the angle between the final vector and the ground, which is just this angle here. And so if you do the tan of theta, you could do any of your trig ratios. So tan is opposite, which is V over hypotenuse, and that helps you calculate your angle of impact here.